Hi there, this is Lucius Laframboise from ENG Suite, and today we are going to continue our discussion on engineering statistics with high capability exemption. So this is really an introduction to Chebyshev's inequality. The reason we paired this up here instead of in our normality series is because as much as we use this when it comes to normality and distribution identification, it really is just capability. So I wanted to throw it in here because we've been doing the math of capability, and this is just sort of a variation of that math. You'll see in a second what's so cool about it. Okay, so as we know, when it comes to capability, we can only use the normal capability if we can assume normality for our data set. Well, what happens if we don't? What happens if we fail a normality test? Well, it depends. You'll probably do a series of normality tests, but there's this thing called a high capability exemption, and the benchmarks are different for every organization, but in this one, I'm going to show you what a high capability exemption even means, okay? So what we're really talking about is Chebyshev's inequality. Now, Chebyshev was a Russian mathematician, and he has this awesome inequality that says that the probability of x, the absolute value of x minus mu, being greater than or equal to k times your standard deviation is less than or equal to 1 over k squared, where p is the probability, x is your random variable, mu is your mean, sigma is your standard deviation, and k is a constant, okay? So what Chebyshev's inequality states in words is the probability that a random variable from an arbitrary probability distribution will be more than k standard deviations away from the mean is less than or equal to 1 over k squared. Let's look back at the math. So the probability that a random variable from an arbitrary probability distribution, that's x. So the probability that x will be more than k standard deviations away from the mean is less than or equal to 1 over k squared. Okay, so x minus mu is the distance that x is from the mean. We know that the probability of this x value being more than k standard deviations away from the mean is less than or equal to 1 over k squared. Okay, so what we're going to do is solve the inequality for k. So all we do is we just pull our sigma, our standard deviation, over to the side, and we get the absolute value of x minus mu over sigma equals k. K is just the number of standard deviations x is away from the mean. But this looks really familiar. That's because it's just a z-score. K, as well as your CPK and your PPK, are just z-scores. Now this one's actually just a z-score. So that means that the probability that x minus mu is greater than k sigma is less than or equal to 1 over z squared. So we know that a z-score is the number of standard deviations that a value is from the mean. But what's so special? We already know that we can calculate the probability of a failing value with a z-score. And that's true, but that's only for a normal distribution. So we have to be able to assume normality. And this is where Chebyshev's inequality really comes in, because Chebyshev's inequality applies to any arbitrary probability distribution. That means we don't need to know the distribution of the data. That's what's cool about Chebyshev's inequality. He's literally saying that for any arbitrary distribution, the maximum probability that x will be more than k standard deviations away from the mean, the maximum probability of that happening is 1 over k squared. Okay, that's great in mathematics. But what does that mean for engineering? Well, we use capability studies to predict the probability of our process producing an out-of-spec part. But that's if and only if we can assume normality. So we can use Chebyshev's inequality to calculate the maximum probability of producing an out-of-spec part, regardless of the distribution, okay? So what we really want to know is, what is the probability that a part will be outside of the spec limits? So we're going to calculate the associated k values, right? Just like with PPK and CPK, what you're really doing is you're just calculating how far your upper and lower spec limits are from the mean. In this case, we take the k value of our upper spec limit and our lower spec limit. Okay? Now that we have that, we know that the probability is 1 over k squared. So we know the probability of a random variable, a measurement, being greater than or equal to the upper spec limit. The maximum probability is 1 over k of the upper spec limit squared. And we know that the probability of our x being less than or equal to, LSL, is equal to, the maximum probability is equal to 1 over k squared. Okay, so how do we use this? Since we want to know the probability the part is outside of the spec limits, either high or low, we just use the higher probability, because that is our higher probability of a failure. We just care what's the highest probability of this happening, right? Okay, so why is it called a high capability exemption? Well, most organizations, if they're using a high capability exemption, will have a critical value. So if k is greater than or equal to that critical value, the probability of producing an out of spec part is so low that we assume the effect of the distribution is negligible. Generally, this critical value is going to be 10, but make sure to check with your organization. Okay? Okay, so why do we still use capability then if we can just do this every time? Well, let's just assume our critical value is 10. And we're going to assume that our sample has a k value of 10. Okay, so our k equals our critical value here. So that means that either the upper spec limit or the lower spec limit is exactly 10 standard deviations from the mean, and the other one's farther away. So k equals 10. So this would be the lowest critical value, the lowest k value we could get to consider a high capability exemption. We don't need to know the distribution. Well, if k equals 10, then the maximum probability of a failing value, regardless of the distribution, is 1 over 10 squared, or 0.01, so 1%, okay? So here's just a restatement of our assumptions here. Our critical value is 10, our k is 10, our probability using Chebyshev's inequality, our maximum probability is 0.01. Okay, now we're going to assume that our data fits the normal distribution, and we're also going to calculate the PPK. Okay, so one thing that we know is we take our spec limit minus mu over 3 times the standard deviation. We can actually split that up to 1 over 3 times the spec limit minus mu over s, which we know that this is just our k. So we can take 1 over 3 times k. So our PPK can also be represented when talking about Chebyshev's inequality as k over 3. So if we take 10, we say, okay, plug in our k, 10, and we get our PPK equals 3.333 repeating. So now let's actually calculate our out of spec condition. So we know that with a k value of 10 and a PPK of 3.333, we can plug in either 3 times the PPK or just the k, because that would be a z-score. We can plug that in Excel to get the probability of a value less than that, right? So we plug that in and we take 1 minus that so we can get the probability of an out of spec, which is basically 0. Excel cannot hold on to a number that small. So what that means is that at a PPK of 3.333, you now have a statistical probability of an out of spec condition so low that the 16 digits that Excel carries can't even show you the probability of that happening. Whereas when you use Chebyshev's theorem, you get a probability, a maximum probability of 1%. So that would be why we use capability. Because if k equals 10, according to Chebyshev's inequality, the maximum probability of failing is 0.01. But according to PPK, the maximum probability is negligible, basically 0. And this is because Chebyshev's inequality is for any arbitrary distribution, while PPK is the known one for the known normal distribution. So Chebyshev's inequality just states that it has to be below 0.01. Not that it is, but that it has to be below that. So how do we calculate our Chebyshev's K value? It's pretty easy. Like we said, just calculate the z-score of your upper and lower spec and then take the maximum, okay? But if you want to just quickly do this, we built an awesome QE Suite function called QE.Chebyshev, and that just calculates your associated K value, which you can then compare to your organization's K critical, or just multiply your CPK or your PPK by 3. That's all you need to do. And Chebyshev, generally you're going to use your sample standard deviation, so you're probably going to use a PPK, but it depends on your organization. Again, make sure you're using your organization's standards. So, just to conclude, Chebyshev's inequality is not a replacement for capability analysis because it doesn't consider the distribution of the data. That's something that's very important and can give you a lot of great insights into what's happening with your data. We'll talk about that a little bit more when we talk about each individual distribution. That's going to be a couple months all on its own. But despite that, it is an incredibly useful justification for passing your validation if you cannot assume normality. That's really when it's going to be the best. You know, take a look at your organization's K critical. If you don't have this, this is always just a great thing to add to make your validation process just a little bit more robust, because if your capability is really above that 3.333, no matter what your distribution is, the maximum probability of a failing part is 1%. And you can modify and change it and do some things. So thank you so much for watching. I hope that Chebyshev's inequality is a little bit easier for you to understand than it is to say. It's not that bad. So thanks so much for watching. Have a great day, and please do something awesome.